Welcome to Anatomy and Physiology's Chapter 25. And in this chapter, we kind of deviate from our normal plan. We're not hopping on to another organ system. In this chapter, we're not really focusing on any particular organ system. Why? Well, it's because of what this chapter is about. We're really talking about all the fluids in your body and things dissolved in fluids. Things like the electrolytes, think charged particles, think sodium, potassium, and things like acids and bases. So we're not really talking about an organ system. We're going to talk about fluids and things dissolved in the fluids within your body. And like always, there's a lot. You have a lot of fluid in your body. Remember, you're almost 80% fluid. And you've seen where you've had fluid. You've been in this class from A&P1 all the way to A&P2. Just think about all the times you saw liquid. Okay. Where? Well, recently you did blood. And you remember there's liquid in your blood. Remember we call that the plasma. Well, that's a type of bodily fluid. And we also talked about fluid around your cells in that extracellular matrix, that environment around the cells. Oh, you remember that's interstitial fluid. Keep going. Not only is there fluid outside of the cells, there's also fluid inside the cell. Think back to A&P1. Remember that's cytosol. Keep going. There's lots of fluid. Remember there's even fluid floating in and around the brain and spinal cord. Remember that's cerebrospinal fluid. Remember, sometimes we can mix up some fluid with fat and things dissolved in fat and send it into a lymphatic vessel. Remember, we call that lymph. And then don't forget all your exocrine secretions, all those chemicals pumped out by exocrine glands. Kind of think things like the pancreas in A&P1. You saw kicking out or secreting lipase and amylase. Or your stomach makes enzymes. All those enzymes are technically fluids. So they're also considered your bodily fluids. So we're going to spend most of this chapter talking about fluids. Why? Well, I mentioned before, you're about 80% fluid. And you have to maintain this level of fluid. When you maintain the appropriate volume, aka the amount, and concentration of liquid in your body, we call that fluid balance or water balance, if you want to talk about water specifically. And you got to keep this fluid balance. You got to keep this appropriate levels of fluid levels and concentration levels in your body, because this is mainly what you are. And you'll notice, or if you think back at all the times we've talked about liquids, whenever there's an imbalance, whenever the volume or the concentration of fluids is off, that could cause problems. So we're going to talk about that. We're going to look at the fluids, remind ourselves about all the different fluids in our body. And then we're going to talk about really what happens when the balance is thrown off and why or what are these fluids doing. You've seen our list of examples of fluids already, so you kind of know what some fluids are doing in your body. Well, let's go through it just to remind ourselves. Remember, a lot of the fluids in your body are basically water. So when we talk about fluids, we're largely talking about water, like I mentioned before, and things dissolved in it. So think way back to A&P1 yet again. What do you remember about water? Think back to your chemistry. Remember, water is the result of a polar covalent bond, meaning that the atoms involved in the water compound are unequally sharing electrons. And because they're unequally sharing electrons, remember this is going to generate a charge. Remember, water has a slightly positive charge closer to the hydrogen end and a slightly negative charge closer to the oxygen end. It is polar. And because it's polar, it could do stuff. Turns out it could transport things. Remember, things with a polar covalent charge can typically dissolve other things by attracting and pulling charges because it has those two poles on it. But again, water could do other things. Turns out water could even help to carry heat, to distribute heat around the body. And we've seen some places where water just acts as a cushion. Remember, your brain is floating inside your skull in some cerebrospinal fluid because that fluid is kind of providing a cushion. I'll keep going. Think back way back to A&P1. Way back to the serous membrane. Remember, your serous membrane made a fluid called serous fluid. And you remember from AMP1, serous fluid, as one of its functions, helps to separate the parietal and visceral layers of the serous membrane and provide some lubrication. We're just talking about functions of fluids, functions of water in the body. And when we talk about water, it follows some weird principles, some weird rules, so to speak. For example, water obeys what we call the principle of mass balance. Simply put, it just means whatever you take in, you're going to have to kick out. Meaning if I drink 5 gallons of water, I'm eventually going to have to lose 5 gallons of water. What comes in must comes out. That's the principle of mass balance. And so what will affect this when it comes to water? What will affect how much you could take in or kick out? Well, I kind of just mentioned, if I drink 5 gallons of water, well, I might have to pee out 5 gallons. So a thing that will affect your fluid balance because of this principle of mass balance is how much water you're taking in. How much water are you ingesting? Think, how much water are you swallowing? But then you also got to think of how you're going to get the water out. Yes, you could pee it out, but there's other ways to lose water. Think sweating. And when do you sweat? Well, you sweat when you exercise. So the amount of physical activity you have will affect how much water will leave the body. It will affect that principle of mass balance. Again, I told you could pee out the water. You know now who's responsible for urination. It's mainly your kidneys. So another factor that will kind of influence your water balance is whether or not your kidneys are functioning properly to remove that water for you. And then we've also saw that there are certain medications that could do it. There are diuretics that could force you to pee and cause you to lose water. And then don't forget your digestive system. Remember, you could drink the water. Turns out you could poop out water as well. It's called diarrhea. You know that from AMP1. So when you talk about water, you got to talk about how do you get it in, ways like ingesting it, and then you got to talk about how do you get it out. Things like sweating, peeing, medicines, or the digestive system. But again, I told you, we're going to talk about more than just water. We're going to talk about things that dissolve in water. If you're noticing from this chapter, you know this chapter actually from AMP1. A lot of this chapter is just us remembering things from AMP1. So think back to AMP1. There are things that dissolve in water. And when they dissolve in water, you know how. It's because those positive and negative charges on water are pulling things apart. So we give names to things. You know by now in anatomy, we name everything. Substances that break apart, aka dissociate into their charged pieces when placed in water, are called electrolytes. An example is, think sodium chloride, aka salt. If you were to drop salt in water, after a while it will break apart. It will dissociate and it will break apart into its positively charged sodium and its negatively charged chlorine. Those are electrolytes. That's all that is. And so as we go through this chapter, we're going to have to talk about electrolytes. But they're not the only things in water. Turns out there are some things in water that do not break apart. They do not dissolve. They do not dissociate. These are called non-electrolytes. They're called non-electrolytes because they're basically the opposites. They are now not having charges. Think back to AMP1. How does a compound not have a charge? What's holding the atoms together? It's a covalent bond, a non-polar covalent bond. And remember, when you have a non-polar covalent bond in a compound, all the atoms are sharing the electrons equally, so there's no charge. And if there's no charge, when I drop you in water, water will not be able to pull you apart. Those are non-electrolytes. And that's all you're seeing in this picture here. It's showing you the exact same example I talked about for an electrolyte. It's salt, sodium chloride. When you drop it in water, again, it's going to break up into its positively charged sodiums and its negatively charged chlorines. That's what electrolytes do. And if you're the result of a non-polar covalent bond, so you have no charges for water to pull apart, well, you will stay your solid compound self. Those are non-electrolytes. But again, We got to go into a little bit more detail. Still talking about electrolytes. Turns out another name for an electrolyte is an ion. But what's the major difference? When we talk about electrolytes and ions, they really come in different forms. When you say electrolyte, you can possibly mean the atomic form or the ionic form. But when you say ion, you're really referring to the ionic form. So what's the difference between the atomic form of these atoms and the ionic form of these atoms? Still, keep it simple. Think about things like sodium and chlorine. Think example like sodium. In the atomic form, if you were to drop sodium, which is a metal, into water, it should technically explode. But we don't talk about, or we really don't focus on the atomic form of sodium, because in your body, you have more of the ionic form. This is the form that simply dissolves. Okay. And how do you know we don't have the atomic form? Just think, when's the last time you saw someone's water exploding? It doesn't happen because we have the ionic forms. So when we say ions, you're just talking about the same atoms, same charged particles, but you're keeping it simple and focusing on the fact that they just dissolve in liquids. And so when we talk about electrolytes, we're going to have to talk about it similarly to the way we talk about fluids. Just how your water follows this principle of mass balance, where what comes in will have to eventually leave, the same thing applies to electrolytes. They also follow this principle of mass balance. They also follow the rule that whatever comes in must come out. And it comes in and out almost the same ways. Again, you could ingest them. Think Gatorade, that has electrolytes, that has ions. You could take them in and then you'll take them out. How? Think of where you saw you could lose ions like sodium and potassium. It was in your urine. So you're going to gain and lose these things very similar to the way you're going to gain and lose fluids. And how much fluid you have is going to be a critical factor in determining your electrolyte balance as well. So let's talk about some of these other things dissolved in water. What else gets dissolved in water? It's acids and bases. Again, you talked all about acids and bases in A&P 1. This is just a refresher. None of this is really new. You know this from A&P 1. We're just reminding ourselves. Starting off with acids. You remember, to be an acid simply means when you're dropped in water, you will dissociate, aka break apart, and release positively charged hydrogen ions. That's all it means to be an acid. When you're dropped in water, you're going to dissociate, aka break apart. And when you break apart, one of the pieces you're going to release is called a positively charged hydrogen ion. That's it. So when you think about any of the strong acids you might know, like hydrochloric acid, that's what you see on the slide. You can see its formulas, hydrogen and chlorine. So when you drop it in water, it will break apart into the positively charged hydrogen and the negatively charged chlorine. That's why hydrochloric acid is an acid, because it's going to release those hydrogen ions. And these hydrogen ions will play a role in helping us to do a lot of things. Again, you know this already. You've seen acid in places before, like in your stomach, helping you to digest food. That acid in your stomach is an acid. It's just something releasing a lot of these positively charged hydrogen ions. Where else do we see acids? You remember, think back to the cell in A&P 1. Think back to organelles like the lysosome. Remember, lysosomes were like big garbage collectors. They could break anything down in the cell. How did they break them down? It was with acid. It was with positively charged hydrogen ions. So having acid in the body is very important because it's helping with a lot of things. But simply put, it's just compounds that when you drop them in water, they'll release positively charged hydrogen ions. But then there is the base. A base is sometimes called an alkaline substance. Alkali is just plural. And again, you know this from A&P 1. You know, when you drop a base in water, it will also dissociate. It will also break apart and release something. But what does it release? Remember, when you drop a base in water, it will release negatively charged hydroxyl groups. OH groups is a hydroxyl group, an oxygen and a hydrogen. That's a base. And remember, these OH groups will gobble up or bind to any positively charged hydrogen ion. So we sometimes call bases hydrogen ion acceptors, sometimes referred to as a proton acceptor. That's it. It's just these OH groups accepting or binding to positively charged hydrogens, because that's what bases do. And an example is bicarbonate ion. Bicarbonate, you can see on this slide, is hydrogen, carbon, and 3 oxygens. You can see when it will get dropped in water, it will just break off a hydrogen and oxygen, which could then go on to bind to a positively charged hydrogen ion. That's what bases do. And it turns out bicarbonate and other bases are part of what we call your buffer system. You know this from AMP1. Remember, buffers help to resist large swings in pH, meaning it helps to resist large changes in your pH. Remember, your pH in your body is close to neutral. It's close to a pH of 7. But sometimes we put things in our body that are on the extreme ends. For example, I don't know about you, I love lemonade. But turns out lemonade is made up of lemons and lemon juice is very acidic, almost close to a pH of 2. But when I drink my glass of lemonade and you check my blood, I'm not going to have a pH of 2. I'm still going to be close to 7. Why? Because I have buffers resisting that large change. And a lot of your buffers are going to be some bases, helping to neutralize acids and keep you closer to neutral. And I told you your neutral's at a pH of 7. You remember from AMP1, when we talk about acids and bases, we have to talk about them in relationship to their strength. And we can measure their strength using the pH scale. And when you measure the strengths of acids and bases, you're not really measuring their strength. You're measuring one thing. You're measuring the concentration of those positively charged hydrogen ions. And so, again, this is just AMP1. Think back to AMP1. You might recall the formula for the pH scale. It's the negative log of the concentration of positively charged hydrogen ions. What does that mean? It's negative. It begins off with a negative sign when you see the formula. That negative sign means that it's in an inverse scale, meaning opposites. Meaning if your hydrogen ion concentration increases, your pH will decrease, and vice versa. If your hydrogen ion concentration decreases, the pH will increase. It's an opposite scale. And not only that, it's a logarithmic scale. It has log in the formula. LOG stands for logarithmic. This is a shrunken scale. You got to think, we're talking about atoms and elements. And in your body, you have over millions of them. Remember, they're microscopic. In one glass of water, you have over 1 million hydrogen ions. And remember, sometimes scientists get a little lazy. It's a lot to write out all those zeros. So we could shrink the scale to a logarithmic scale. So that one change in the scale will really represent a 10-fold change in the concentration of hydrogen ions. What does that mean? It means, for example, if I have a solution that has a pH of 3 and I compare it to a solution with a pH of 4, that solution with a pH of 3 is 10 times more acidic than the one with a pH of 4. It has 10 times the hydrogen ion concentration than that pH of 4. We're just shrinking the scale. And you might recall, the scale is not that big. It goes from 0 to 14. Again, just break it down. Remember, it's an inverse. So if I have a low hydrogen ion concentration, I'm going to have a high pH. So we say if you have a pH greater than 7, you're a base. Why? Because you have very little hydrogen ion there. Why? Maybe you had hydroxyl groups from bases gobbling them up. That's why pH greater than 7 are bases. Well, on the other hand, if you have a pH less than 7, remember that's a low pH. What you're really saying is you have a high hydrogen ion concentration. That's why you're considered an acid if you have a low pH, because you're releasing lots of hydrogen ions, and that's what acids do. And if you notice, I'm jumping all around 7. You're either above 7 for a base or below 7 for an acid. Oh, what happens at a pH of 7? At a pH of 7, you're neutral, meaning the concentration of hydrogen ions is equal to the concentration of hydroxyl ions, meaning you're going to have an H, positively charged H, aka hydrogen, plus an OH. Oh, what do you get when you add 1 oxygen to 2 hydrogens? Oh, that's called water. At a pH of 7, you have pure water. That's neutral. Why? Because the concentration of hydrogen ions is equal to the concentration of hydroxyl ions, and they will bind to each other to form water. That's why water has a neutral pH. And that's acids and bases. Again, none of this was new. You knew this already from A&P 1. So let's go back and talk about our major topic for this chapter. Let's go back and talk about water. Now you kind of got a hint about some things that water is responsible for. So now we could talk about some other references in terms of water. Another reference or another feature we talk about when we talk about water is something called your total body water. Like always, it tells you in the name. This is the total amount of water in your body. It's the amount of water giving you your body's weight. And like usual, we know some average numbers. For an average male, and on average, they're saying a male is about 150 pounds. That's what usually they mean by 70 kilograms. Think about 150 pounds. Well, for a standard male, for a male who's 150 pounds, of that 150 pounds, about 60% of that is water. That is the total body water. But again, this is just based on average numbers. Like I always tell you, if you're a little bigger or smaller, it will vary. So you'll see the total body water will vary based on things like gender, where males are on average bigger than females. But if you are a bigger person, you have a bigger body mass or body mass index, you might have more water. Or even other things like your age will determine it, or how much of a certain tissue you have. Fat is actually really watery. So if you have a lot of fat, you actually might be retaining more water. So yes, there's an average total body water number, but it could vary based off certain variables. Again, gender, age, your body type, etc. And when we talk about the water, all this water in your body, your total body water, you got to think about all the different places we found it. Think back to that first slide, all the places you found water. We're just reminding ourselves. Remember, we found water outside of our cells, in the environment around our cells. Remember, we call that environment around the cells the extracellular matrix. And in that extracellular matrix, in that environment around the cells, there is fluid. We call it interstitial fluid, or the overall name for it is extracellular fluid. That's the real name for fluid around your cells. It's extracellular fluid. And of that extracellular fluid, some of it is forming your blood as plasma, but some of it is just that regular fluid around the cells, interstitial fluid. And that's all you're seeing in this picture. You'll see some extracellular fluid, fluid around the cells, that's some plasma fluid or just plain old fluid around the cells, as well as intracellular fluid, fluid inside the cells. And you can see from the picture in the previous slide, most of your extracellular fluid is the interstitial fluid. Most of the fluid outside of the cells is just in that environment right around the cells. The majority of your fluid is the intracellular fluid. Most of your fluid in your body, up to about 60% of the fluid in your body, is inside your cells. Because remember, you're mainly fluid. Because now you know why. It's mainly what's making up your cells. So we're going to have to look at these types of fluids. For example, on this slide, we're going to have to look at things like your interstitial fluid versus your plasma fluid. Turns out, all the extracellular fluid in your body is not the same. For example, your plasma fluid actually has more protein than your interstitial fluid. Remember, you know this from when we did blood. You have lots of proteins in the plasma. And when you compare that to the fluid outside of the cells, the interstitial fluid, it actually has virtually no protein in it. But they also have some other differences. Turns out we could compare extracellular fluid overall to intracellular fluid. Turns out when we look at extracellular fluid, it has a higher concentration of ions. Think sodium ions, chloride, calcium, that bicarbonate ion. You have a lot more of them outside the cell. You have a lot more of them in the extracellular fluid than you do in the cytosol. And if you were to flip it, what do you have a lot of in the cytosol? What do you have a lot of inside the cell? Well, it's going to be proteins. Proteins, as well as some other ions like potassium, magnesium, even some sulfate. You have a lot of these inside the cell, in the cytosol, when you compare it to outside the cell. So it turns out all the fluid in your body is not the same. You'll have different concentrations of different things dissolved in the water compared to where you're looking, inside the cell versus outside. And even when you're looking outside, it's comparing the interstitial fluid directly around the cells compared to the fluid in your blood. That's all this chart is showing you. You have different levels of all these particles in your fluid, depending on what fluid you're looking at. And so, water, you might recall from AMP1, can move. And because we notice that the concentrations in different water areas are different, we might see water move from one part of your body to another. We might see water move from one compartment to another. So we're going to have to talk about that. And yet again, you know some of this already. We're talking about moving liquids. Think back to things like blood and blood vessels in this class. Remember what was a driving force for fluids in your body? It was pressure changes. You know this already. You remember there's a force that pushes fluid either out of a cell or away. Remember that pushing of fluid is what we call the hydrostatic pressure. This is water moving away from an area. You're pushing it away. That is hydrostatic pressure. But again, think back to blood. Remember, there's a pressure, there's a force that pulls and attracts water. When you pull water towards you, that's an osmotic pressure. Make sure you know the difference. Hydrostatic pressures push water away from an area. Osmotic pressures pull water towards an area. And again, this is all based off the concentration of solutes. Remember, water is a powerful solvent. It loves to dissolve solutes. So it will move based off the concentration of solutes. Remember, we have another name for concentration. It's called osmolarity. Osmolarity is simply the number of solutes present in a solution. But that sounds a lot like concentration. So when water moves, it will move thanks to pressure changes, but also thanks to osmolarity, thanks to concentration of your solutes. But again, we're going to have to look at this in a little more detail. First, starting off with those two major pressures, hydrostatic pressure and osmotic pressure. Let's start off first with the hydrostatic pressure. Remember, this is the pressure that pushes water. You've seen this already. You've seen hydrostatic pressures like in the glomerulus, in the capillaries of the glomerulus. Remember that hydrostatic pressure of the glomerulus was the pressure pushing the water out of the blood vessels. It was telling you in the name, it's the hydrostatic pressure. And you remember for our kidney, you push the water out of the glomerulus capillaries into that space called Bowman's space. That Bowman's space wasn't inside of a cell. You were pushing it into a space outside of your cells. You push the fluid from the plasma, from the capillary, into an interstitial space. You forced it to become interstitial fluid when you were making your urine. So no matter where you look in the body, if there is a hydrostatic pressure, it's a pressure that's going to be pushing fluids away, outside of something. And from our kidney chapter, we saw that in most cases, you're going to be pushing that water outside of blood. You're going to be pushing out all that liquid, that water outside of your plasma into the environment around the cells. And it normally goes that way. And if you're wondering, what if the hydrostatic pressure in my interstitial fluid was high? Would I push water now back into the blood? No. If you're putting water into the blood, that's a pulling pressure. That's osmotic pressure. you'll still have a hydrostatic pressure in the bloodstream. So you'll always only push that liquid out of the blood. If anything, you'll just diminish how much you kick out, but you'll still kick it out. Why? Because this is a hydrostatic pressure. Kick it out, push it away. But again, other pressures. Remember, there's that pulling pressure, attracting the fluid somewhere. Remember, that's your osmotic pressure. And again, we saw osmotic pressure when we did blood, when we looked at plasma. Remember, there was a protein in your plasma that helped to pull water into your plasma. Remember, that was albumin. Albumin was helping to cause an osmotic pressure. It was helping to pull that water into the bloodstream. But again, remember, you have large different pockets of fluids. For example, what would happen if we compare the extracellular fluid and your intracellular fluid, your cytosol? Turns out they would have almost the same concentration. So it turns out water doesn't really move that much between the extracellular and intracellular fluids. Why? Because they're isotonic. Remember, this chapter is a lot of AMP1. Remember when we talked about water moving, that was osmosis. And when we talked about osmosis, we also talked about tonicities, having different concentrations inside versus outside the cell. And remember when you talked about tonicities, we saw 3 different types. There was an isotonic solution, hypertonic solution, and hypotonic. When we compare intracellular fluid, aka cytosol, to extracellular fluid, they have very similar concentrations, almost equal. They are isotonic to each other. So when we talk about water moving, you're not really going to move that much water between outside and inside a cell. Why? Because they're isotonic, having the same concentration of solutes. So water's not really going to move that much. But your body does alter solute concentrations. You could add or remove solutes from different areas in your body using certain pumps in the plasma membranes of your cells. So you can alter solute concentration. And if it's altered, well, then you might change the osmotic pressure and cause an attraction of water. You'll cause water to move because solute concentrations have moved. Remember, that was osmosis. So again, we're just reminding ourselves about different topics from AMP1. For example, still talking about water moving, and we know it's going to move based off ion concentration differences, solute concentration differences. And you remember there was an isotonic solution. There are no differences there, so we're not going to talk about that one. We're going to talk about where there are differences so that we can see water move. You know this from AMP1. First up is a hypotonic solution. Think back to AMP1. Remember, a hypotonic solution is a solution that is less concentrated than the inside of a cell. And think back to AMP1, you might recall dropping a red blood cell in a hypotonic solution. Remember, when you drop a red blood cell in a solution that is less concentrated than it is, water is going to move. Remember, water wants solutes to dissolve. So all the water in that hypotonic solution is going to look inside the cell and see there is more to dissolve inside the cell. So guess what's going to happen? Think back to AMP1. What happened when you dropped a red blood cell in a hypotonic solution? It swelled up. All the water rushed into the cell because the cell had more solutes to dissolve. The water swelled up. It gained water weight. And you remember, some cells could swell so much that they pop, they lyse. So a lot of this, nothing is new on this slide. You know this from AMP1. A hypotonic solution is less concentrated than the inside of a cell. So when you drop the cell in the hypotonic solution, all the water will rush in. The cell will gain that water and it will swell and possibly pop. And then there was the hypertonic solutions. Remember, a hypertonic solution is more concentrated than the inside of your cells. So when you drop a red blood cell, for example, in a hypertonic solution, now all the water inside the cell is going to look outside and see there's more to dissolve. So what's going to happen? All the water is going to leave the cell. Remember, when you drop a red blood cell in a hypertonic solution, it's going to shrivel up. Oh, you remember, you might have recalled this fancy word for cell shrinkage or shriveling. Remember, it was called crenation or crenates. So when you drop a red blood cell in a hypertonic solution, all that water is going to leave the cell and cause the cell to shrivel up. It'll cause the cell to crenate. So you see, you know this whole chapter just about from all the work you've been doing in anatomy and physiology in A&P1 and A&P2. So now you remember how you move water into and out of a cell. It's all based off the tonicity, the concentrations of those solutes. You're just watching osmosis. But again, remember, you have different pockets of water. Now you know how to move water between the cytosol and interstitial fluid. Remember that there's also differences between interstitial fluid and plasma. Now we got to talk about moving water between the two types of extracellular fluid, between plasma and interstitial fluid. This movement is going to be really based off those pressures, hydrostatic pressures and osmotic pressures. And remember, plasma is part of your blood. So we're really talking about moving liquids between your blood and blood vessels and the environment around the cells, the interstitial fluid. You know this. Think about the glomerulus in the kidney. You know, to get water out of a blood vessel, like an arterial artery or capillary, you need hydrostatic pressure to push it out. So high hydrostatic pressures are what dominates in those arterial blood vessels. Think arteries, arterioles, and capillaries. They all will have high hydrostatic pressures to help push that water out. But what about veins? Remember, veins kind of are the opposite. They receive and drain fluids to bring it back to the blood. So how do I get fluids into something like a vein? Well, you're going to have to pull it into the vein. You remember that pulling pressure is your osmotic pressure. So when we look at things like veins and venules, well, they'll have a high osmotic pressure to help pull that water into the blood vessel. And then you'll be able to circulate it around. So these are the two major ways you're moving liquids between the plasma and interstitial fluid. Push it out with hydrostatic pressure, pull it in with osmotic pressure. And yes, these same two pressures, hydrostatic and osmotic pressures, can influence to a smaller degree compared to tonicities. It can direct the movement of water between the plasma and the cytosol, intracellular fluid as well. And again, it's the same directions. Hydrostatic pressures push, osmotic pressures pull, but it's not the driving force between plasma and cytosol. We saw 2 slides back. It's more of osmosis related to concentrations of solutes that will cause the movement between the plasma or extracellular fluid and the intracellular fluid. And these are all related. Turns out if you affect the concentration or water levels in the plasma, it will have an effect on the water levels or the concentrations in the extracellular fluid around the cells, interstitial fluid, and possibly some of the fluid inside the cell as well, the cytosol. So we're going to have to talk about it. For example, what changes will you see if you see the plasma has gained water? Let's say you had a whole weekend of partying and you went to the hospital and they hooked you up to an IV bag to give you water. What would that do to the rest of the water in the body? Well, again, think first you're going to have to get that water out of the bloodstream. How do we do that? Remember, that's hydrostatic pressure. So whenever the plasma gains water, your hydrostatic pressures will increase, and that will begin to help push some plasma out of the blood. But at the same time, you got to think, if I'm having more water, it's also more dilute. It's going to be approaching that hypotonic range. That osmotic pressure is going to decrease. So you're going to have a higher hydrostatic pressure in the blood when the plasma gains water, and you're going to have a decreased osmotic pressure because there's a lot of water. Both of those things are going to cause you to lose water out of the blood. You're going to be pushing out the water and not pulling it back in. Why? You gained too much already. So these are some changes you're going to see when your plasma gains water. And then the opposite is going to happen when you have little water. When you have a little water, or what we call a deficit of water, meaning not enough water, well, that's dehydration. So what happens now when you're dehydrated, when there's little water in the plasma? Well, there's little water, so the hydrostatic pressure is going to decrease because you don't want to lose that water from the blood. And because there's little water in the blood, you're going to have a higher concentration of solutes. It's going to seem more hypertonic. So your osmotic pressure is going to increase. You're going to pull that water into the bloodstream. That's why when you're dehydrated, you might seem like you're losing weight. It's because you've pulled all that water from around the cells and you've put it in your bloodstream to keep your cardiovascular system working. How did you pull it into the bloodstream? You dropped your hydrostatic pressure and you increased your osmotic pressure. So that's how ways water is going to move from the different compartments in your body. And that's all you're seeing in this picture. If you drink water, you're going to put it in your bloodstream. You're going to increase your hydrostatic pressure, drop your osmotic pressure, and push that water out. And when you're dehydrated, it's the opposite. When you're dehydrated, the hydrostatic pressure will drop, osmotic pressure will increase, and you'll pull the water into the blood. Why? Because you got to keep the heart pumping. You got to keep that blood circulating because your cells need oxygen and nutrients. So you're going to maximize that water in the bloodstream. So now that you know how water is moving at the cellular level and microscopic levels, we could kind of zoom out a bit and look at you overall. Look at you as the organism globally and talk about how water moves. When you talk about global, the organism, the human, when you talk about water movement, it's either coming in, you're gaining it, or going out, losing it. So now we could kind of relax a little bit and talk about some water losing and water gaining. And like always, there's lots of factors, especially when it comes to losing water. It's really simple to think about how you gain it. You could drink it. You even make some of it in chemical reactions. But turns out there are lots of ways to lose water. So we're going to have to talk about some of the ways to lose water. Well, some ways you already know. You know you can lose water in your urine. And turns out your kidneys will force you to lose water, aka force you to make urine despite how much water you're taking in. Why? Think back to our urinary system chapter. Remember, part of your urine is you excreting things into the urine you don't want, like waste, like certain toxins. So no matter what, every day you should have some urine, no matter how much you're drinking, because your body has to filter out toxins. We call this amount of water loss obligatory water loss, because you're obligated to lose this much water because you have to get rid of toxins. Remember, if your kidneys shut down, you need to do dialysis because you need to remove these toxins. But there are other ways to lose water. Well, yeah, we got to talk about it. It's called diarrhea. In diarrhea, you usually have loose, watery stools because you can lose water. You can lose water in your feces. And sometimes you could sense this. It's noticeable when you have diarrhea. You could sense when you're losing water in your feces. So we call this a sensible water loss. But there are some types of water loss that are kind of hard to sense. It turns out, just by breathing, you're losing water. Kind of think, everyone's been a kid where we breathed on a piece of glass or a mirror and we drew our name in it. Why? How are you able to do that? Well, it's because when you breathed on that glass or that mirror, you left some water. Because in your breath, when you breathe out, there is some water. So even just by breathing, you're losing water. And it's kind of hard to sense that loss because you're really focusing on the air leaving your body. You're not really focusing on the water leaving. So we call this an insensible loss. So when we talk about water balancing and following the principle of mass balance, where we talk about things coming in and coming out, well, you got to think about all these ways water is coming out. You're having to force water out no matter what to clear toxins, obligatory water loss. You're going to lose water in places like your feces that you could sense, sensible water loss. You're going to lose water in things like the air you breathe out, or even the water evaporating from your body when you sweat and you can't really sense it. These are insensible water losses. So there are multiple ways to lose water. But then what about gaining water, getting the water? We know, yes, we can ingest water, but there are other ways to get water. Turns out your body can make it. You make water in all of the catabolic reactions that occur in your body. You remember catabolic reactions, sometimes called decomposition reactions, are when you break things down. Turns out when you break a lot of things down in your body, you're going to produce water. So when we talk about water gains, there are at least two ways you're getting it. Yes, you could ingest it, take it in by drinking or eating, but your body could also make the water. So again, when you talk about water balance, you got to talk about that principle of mass balance, where you're going to have to account for what comes in, coming out. You got to account for all the ways you could get water in and all the ways you could get water out. And again, we're going to have to go into detail. We know we could get water in from ingesting it. Think drinking water. That's ingesting water. And sometimes you're going to feel like you're forced to get water. How? It's called being thirsty. So we're going to have to talk about that. Turns out, your body is what's causing you to get thirsty. It's part of a feedback mechanism we call the thirst mechanism. And it's pretty much a specific type of negative feedback. So kind of remember the players or the variables involved in negative feedback. Remember, there has to be a receptor to notice the change in the stimuli. There needs to be the control center to come up with a plan. And there needs to be the effector to put the plan into effect to restore homeostasis. Well, this is kind of what happens when you're thirsty. You're thirsty because your body is low on water, and you're going to go through some steps to raise your body water level back up to restore your water homeostasis. So let's go through that. How does your body know, first of all, when you're dehydrated? Well, you got to think, when you're dehydrated, where you're not going to have the water. Think about the places where we have water, like your blood, like your plasma of your blood. Well, if there's not a lot of water in your plasma, well, your plasma is going to get highly concentrated. The osmolarity, aka the concentration, is going to increase. There's going to be something to notice that change in osmolarity. It's going to be a type of receptor we call an osmoreceptor. So they're one of the receptors to first notice when you're dehydrated. How? They're going to notice your plasma is a little bit more concentrated than usual. But that's not the only receptor. You got to think, when you have water in your plasma, that's contributing to your blood volume. And you remember, your blood volume affects your blood pressure. So if you're low on water, well, you're going to have less water in the plasma. So you're going to have a lower blood volume and a lower blood pressure. Remember, there are receptors that can notice or measure pressure changes. Remember, those are baroreceptors. So if your baroreceptors notice your blood pressure drops, an indication is that you might be dehydrated. So these are two receptors that could help to notice when you're dehydrated. But then what? Who's the control center? Who could help you out? Well, it depends on the receptor. Turns out when your osmoreceptors notice your plasma getting concentrated, well, they're in the hypothalamus. So your hypothalamus could help to release some hormones to restore homeostasis. But on the other hand, if it's a baroreceptor, those baroreceptors are sometimes stimulating cells, like cells in the kidney. Like cells that can help to raise the blood pressure when it gets too low. You gotta remember the juxtaglomerular complex, which are juxtaglomerular cells, your JG cells. Remember, they release renin, which will help to trigger the renin-angiotensin-aldosterone system. And you are not going into all that detail because we already did it in urinary system. You just remember that the end result was you getting some angiotensin 2 that could help to raise the blood pressure. And so this is how you're going to help to notice and hopefully help to restore blood volume changes and water changes overall. And that's what you're seeing on these pictures. When you're thirsty, it's because you're dehydrated. And what's happening? Well, in one case, osmoreceptors can notice the plasma is getting concentrated. Then the hypothalamus will trigger the thirst to get you to restore your water levels. At the same time, baroreceptors, which is what you're seeing on this slide, can notice that your blood pressure is dropping, and they'll stimulate those JG cells in the kidney to release renin and trigger the renin-angiotensin-aldosterone system to raise the blood pressure. Some ways will include holding on to body water and also triggering thirst. This is all that's happening. Your body, remember, your body thinks you're stupid, and it will try to protect itself even from you. When you have your night of partying and drinking and staying up all night, your body knows it's getting dehydrated, so the next day it's going to tell you to be very thirsty. And now you know the details on how. So we could put it all together now. When we talk one more time about water balance, we got to think about all the ways we gain and lose water. You know now how all the ways you're going to lose it. And you know at least one way you're going to gain it. You know you could get it from chemical reactions. And you could also drink it and ingest it. So let's say in a typical day, if I wanted to think about my water balance, how much water am I going to lose and gain? Remember, in anatomy, we presume we know some averages. On average, a person typically loses about 2.5 liters of water. Think of all the ways you're going to lose it, not just peeing. You're going to lose it in your breath, and you breathe constantly every day. And you're going to lose it in things like your sweat. So on average, every day, a person loses about 2.5 liters of water. So to balance that out, you're going to need to form or get 2.5 liters of water. No, you don't have to drink 2.5 liters. Why? Because you remember, you're going to make some in your catabolic reactions. But you'll also get some from the food you eat. And then the rest is what you're going to have to drink in. And this is going to vary from person to person. Remember, like always, these numbers are averages. And it's going to be based, in this case, on your level of activity and your body's metabolic rate. So if your body's not doing that many chemical reactions, well, you're not going to form that much water. If you're not doing that much exercise, you're not going to lose that much water in sweat and heavy breathing. So a lot of the variables go into how much water you're going to need to balance out all the water you're losing. But don't worry, don't stress too much. Why? You remember, if you know a lot of anatomy, you could take advantage of it. You know, if you get dehydrated, if you're losing water, you simply just have to replace it. And you know from AMP1 and 2, your body is a little on the salty side. It has some stuff dissolved in the fluid. So if I want to help you out, I'm going to give you a fluid that's isotonic to your body. You remember, or you might know, medicine has a way of giving people fluids directly into the bloodstream. It's called an IV. Stands for an intravenous. IV stands for intravenous. If you need fluid, I could give you an IV line, an intravenous line. I could hook up a line of fluid directly to the bloodstream. And I'm going to have to make sure that fluid is isotonic to your own bodily fluid. If I'm hooking it up to the bloodstream, it needs to be very isotonic to the plasma, as well as some of the other extracellular fluid in the body. And I'm going to have to control how fast I give you the water. Not going to want to give you the water too fast where your body might not be able to control it. So now you know some basics on water gains and water losses and how a medicine can help. But then, like usual, we're going to have to go into a little bit more detail. Again, a lot of this you already know. This whole chapter is almost us revisiting stuff we've talked about already. Again, we're still talking about balancing your fluid levels, your water levels. Well, one way your body is going to do it, besides your baroreceptors and the juxtaglomerular complex with renin, angiotensin, and aldosterone, well, another way it's going to do it is with other hormones other than aldosterone. You already know these hormones. Like on this slide, another hormone that could control your water levels is antidiuretic hormone. You remember, where does this hormone react? Remember, it acts on the cells in the kidney. Remember, it acts on the cells in the distal convoluted tubules and the collecting ducts. You remember when you're dehydrated, you're going to release this hormone and it's going to go to the distal convoluted tubule and the collecting ducts and force the insertion of aquaporins, force the insertions of integral proteins into the plasma membrane to allow for cells to cross. To allow for water to cross. So again, go through the details. This is again negative feedback. So if I were to increase my antidiuretic hormone levels, it would cause me to hold on to water and increase my body water levels while decreasing my urine levels so I don't lose it. And then on the other hand, if I'm highly hydrated, if I have a lot of water in my body, I'm going to decrease my antidiuretic hormone levels, which will cause no insertions of these aquaporins, which will allow me to urinate out urinate out the water, eliminate the water in my urine, and decrease my water levels. So it's all this type of negative feedback. If your water levels get too high, you'll do things to drop it. And if it's too low, you'll do things to raise it. And again, you know all these things that you're going to use. You're going to use different hormones, like antidiuretic hormone. And it isn't even the only hormone. We've already seen things like aldosterone could affect it. Remember, aldosterone will cause you to hold on to sodium and water while you lose potassium. And we saw things like atrial natriuretic peptide coming from the heart, which does something similar, causes you to lose water in this case by causing you to lose sodium, which will drop your blood volume and drop your blood pressure so your heart gets a rest. There are lots of hormones that could affect your fluid balance levels. So let's try to put it all together in a complicated way. Think about all the ways you gain and lose water and how you're going to fix it. On a daily average weight, you're normally going to gain and lose water. And this is going to affect things like your urine output. You know, on days when you're dehydrated, you're going to get highly concentrated in the plasma and you're going to kick out less urine. While when you're having very hydrated days, you're going to have a lot of water in the plasma and you're going to kick out a lot of that water in your urine to help restore the osmolarity. So let's go through it. Let's go through some ways in which we fix imbalances and remember the detail. This is just us rehearsing a lot of these things we've already talked about. Again, let's talk about dehydration. What happens when your body's water levels drop? You know, when the water levels drop, that's going to be interpreted as a high concentration. And it's going to be interpreted as a high concentration in your extracellular fluid around the cells, aka think the plasma. So again, summarize it. We're dehydrated. First of all, why? It's because you lost water. How? Well, maybe you were highly active and sweating. Remember, you're going to lose water that way. Or remember, you could lose it in the feces. Remember, you could be dehydrated. But what comes up comes down. If I could poop it out, it could also come out the other way. It's called vomiting. Oh, yeah, when you vomit, you lose some water that way. And don't forget, you could pee it out. You're losing water lots of ways. And again, when you lose the water, your plasma water volume will drop. At the same time, its concentration is going to increase. And this is going to have an effect. You're going to have way more solutes. It's going to somewhat turn into something similar to a hypertonic solution. So water is going to be attracted to it. It's going to pull water in. How? Because it's increased the osmotic pressure, that pulling pressure. And as that pulling pressure increases, as that osmotic pressure increases, well, you're going to be pulling that water from other places you have that water, like inside of the cells. That's what's happening when you're getting dehydrated. That increased osmotic pressure and all that concentration in the plasma is pulling all the water out of your cells. Your cells are crenating when you're dehydrating. And this will lead to imbalances, these solute imbalances, which can be fatal. While on the other hand, if you're overhydrated, you're going to have something similar to a hypotonic situation going on. Again, let's think about it. You're overhydrated. You have a lot of water. So you're going to have a lot of water in places like your blood. And if you have a lot of water in the blood, in the plasma, that's going to increase the hydrostatic pressure in the plasma and decrease the osmotic pressure in the plasma, which will force you to kick the water out of the blood and force it around the cells. And the cells will see all the water and it will rush in using osmosis and cause the cells to swell. That's why when you drink a lot of water after being dehydrated, you might notice you look a little chunkier. It's because your cells are literally swelling, because it's like you're in a hypotonic solution, because you've introduced all this water into the body. And if you have a lot of water in the body, that's actually a problem. For example, some people secrete abnormal amounts of antidiuretic hormone. Or on the other hand, some people take in extreme amounts of water. This is called water toxicity. Having too little or too much water could be a problem. Why? Turns out, if you're overhydrated and you have water toxicity, this would lead to you kind of seeming dilute, like you don't have enough sodium. It's called hyponatremia. Hyponatremia is a low sodium ion level, usually caused by hydration. You're diluting your own bodily fluids. This will cause all your cells in your body to swell, like the cells in your brain. And when the cells in your brain swells, we call that an overall brain swelling called cerebral edema. So if you have water toxicity, it leads to hyponatremia and cerebral edema. And when the brain swells, well, then you're going to get a lot of nervous system problems. Mental status changes. You might get a little delirious, might even slip into seizures or comas and die, just by overhydrating yourself. This is in extreme cases, but it can happen. There are other imbalances to your fluid homeostasis. Again, think about all the places where you have water, like your blood. Well, it turns out if you lose blood, that will cause a problem. Blood loss will cause you to have a hypovolemia, meaning a low fluid volume level, because you're losing some of your fluid, because you're losing blood. You're not going to see the same changes in concentrations when you're losing blood, because you're not just losing water and you're not just losing solutes. You're losing blood. You're losing the mixture. So the concentration differences or ratios are going to stay the same. So you're not going to see the same effect in a hypovolemia problem caused by things like blood loss. What you're going to see is more of a cardiovascular problem. Remember, you have to keep water in the blood to allow your cardiovascular system to work properly. So if you're hypovolemic, one thing you might notice is shock. Shock is when your cardiovascular system, your heart and blood vessels, aren't delivering enough oxygen and nutrients to your tissues. Why? Well, one reason is because you don't have enough blood to pump around. One reason is hypovolemia, which can be caused by blood loss. On the other hand, if you have hypovolemia, well, you can have hypervolemia. You can have too much water in the blood. Too much bodily fluid, period. Not just too much water. Again, this is a lot of fluid, but it's not going to really change the concentrations, because it's, again, still a lot of blood. Kind of think receiving an extra blood transfusion for no reason. You're still going to have a mix. You're going to have a solution of your solvent, water, and solutes. So you're not going to see, again, the same changes. When you have hypervolemia, just a lot of fluid, period, not just pure water, you will still get swelling. You will get edema. But this is edema not caused by cells swelling up, because remember, there are no concentration differences. This is just edema caused by interstitial fluid. The fluid is just going to sit around the cells, not necessarily enter the cells. So you don't have to worry about cell lysis in the cases of hypervolemia. You're just going to worry about overall general swelling, edema. So now you know about regulating your body water levels. So now we're going to switch gears. Now we talked all about water. Remember, this chapter is about water, electrolytes, etc. Now we got to talk about that. We got to talk about the electrolytes. Remember, those are charged particles. Think of all the special charged particles we've seen in anatomy. One major one was sodium. It turns out sodium ions, remember, are more abundant. They're more in concentration outside of the cell. You have more sodium in the extracellular region, more sodium outside of the cell, and very little sodium inside of the cell. Remember, when you have different amounts of things in different places that are connected, we call that a gradient. You have a steep gradient for sodium when you compare the cytosol's concentration to the extracellular fluid. This is why sodium is so important for doing things like generating action potentials, because it's going to be a huge swing. When we talk about depolarization, remember that's for you going from things like negative 55 millivolts to positive range millivolts, almost up to positive 30 millivolts. You have this huge swing because you were relying on this large gradient, because that difference inside versus outside of the cell for your sodium amounts is huge. And you have a lot more of it outside of the cell than you do inside. So inside of your cells, your sodium levels are low. But how? Turns out you force your sodium levels to be low inside the cells. And you know how. Remember, what's one way to have sodium cross the plasma membrane? Remember, it's via active membrane transport using a pump we call the sodium-potassium ATPase. Think back. Remember this. Remember, the sodium-potassium ATPase kicks out 3 sodiums for every 2 potassiums it lets into the cell. So it's kicking out a lot of sodium. And this is maintaining a low sodium concentration inside of the cell and a high sodium concentration outside of the cell, and establishing this electrochemical gradient for just sodium. And so, like I mentioned before, when we talk about things like depolarization and making action potentials, we're talking about things like opening up voltage-gated sodium channels. And when we do this, we're going to have a large rush of sodium rushing into the cell, bringing their positive charges with it and causing the cell to become positive along the inside of its plasma membrane, aka depolarization. This is why sodium is so important, because it's a large difference when you compare the concentration outside of the cell versus inside. And whenever we change that difference, we see weird things like depolarization leading to sparks of electricity we call action potentials. And so your body spends a large amount of time regulating your sodium ion concentration, regulating your sodium homeostasis. It has to stay within those ranges where you have a lot outside and very little inside the cell. So like usual, we got to follow this principle of mass balance, where what comes in has to be balanced out by what comes out. So when we talk about regulating sodium, we got to think about things that cause us to reabsorb or hold on to sodium, and things that cause us to secrete or get rid of sodium. You already know this. We're talking about hormones. Hormones like aldosterone. You know aldosterone causes sodium reabsorption and potassium secretion. So aldosterone and also angiotensin 2 causes you to hold on and increase your sodium levels. While there's going to be a hormone that will drop it. You know it. It's atrial natriuretic peptide coming from the heart. Remember, this will cause you to secrete or inhibit sodium reabsorption and water so that you will pee it out and drop your blood volume levels and your blood pressure so your heart could get a rest. These 2 groups of hormones are balancing and maintaining your sodium homeostasis. And that's all you're seeing in this picture. And it's all thanks to the kidneys. Remember, your medulla has that osmolarity difference between the medulla and the cortex to help your kidneys sense your sodium levels using that juxtaglomerular complex. And so when your sodium levels outside of the cells drop, you could do things like release angiotensin 2 and aldosterone to raise it. Or on the other hand, if your sodium levels get too high, your blood volume might increase and increase your blood pressure. So your heart will release atrial natriuretic peptide to drop those things. You have even a balance for your sodium levels. And yes, even for sodium, things could go wrong. You could get imbalances in your sodium ion levels. It's super simple. You either have too much sodium or too little when we talk about imbalances. When you have too much sodium in your bodily fluids, we call that hypernatremia. And on the other hand, if you have too little sodium in your bodily fluids, we call that hyponatremia. And how do you get them? You know the answer. You know when you're dehydrated, little water in the body, you're going to have less water in your plasma and more of the solutes, like sodium. So you tend to see hypernatremia when someone is dehydrated. And you remember when you're overhydrated, you have too much water in the plasma, you're going to look dilute, like you have very little ions, like sodium. So you tend to see hyponatremia when you're overhydrated. So we see your water levels in your body seem to affect your sodium levels, but it's not directly. The amount of water in your body does not affect the number of sodium ions you have. It's just affecting the concentration, talking about how much is dissolved in a certain amount of water. So if you have less water, it's going to seem like you have more sodium, but you really don't. It's still the same amount of sodium. It's just less water. And same thing for the opposite. When you have a lot of water, when you're overhydrated, you have more water to dissolve the sodium. So it's going to seem like there's less sodium, even though the same number of sodium is there. And that's all this slide is talking about. It's a relative relationship based off concentrations, based off solutes dissolving in solvents, things like sodium dissolving in water. But again, it's not the only ion. It's not the only charged particle. Remember, another very important charged particle is potassium. And you know you have a lot of potassium inside the cell, and you know it's thanks to that sodium-potassium ATPase. As you're kicking out those sodiums, you're letting in potassium. This is why you have a lot of potassium inside of the cell. And this is why potassium is important. It also has a huge gradient, a concentration gradient, where there's a large difference between what's inside and outside the cell. So again, when you do things like making action potential, you're going to rely on this. Turns out when you open up potassium channels and kick out potassium, it was going to be a lot of potassium getting kicked out. You're going to lose a lot of positively charged ions. So the cell's going to become negative on the inside. It's going to repolarize. Now you're knowing why your body's relying on these ions. It's because they have a huge concentration gradient. Again, that's all you're seeing on this picture. It's just showing you repolarization. When you open up potassium channels and kick potassium out of the cell, you're going to kick out a lot. And that's how you're going to drop from that positive 30 millivolts all the way back down to your negative 70 millivolts in cells like your neurons. And again, we're going to regulate our potassium levels with hormones. But there are some hormones that regulate potassium levels we did not talk about. Let's focus on those. There are hormones that actually cause you to raise your cellular potassium levels. It's actually insulin and epinephrine. Insulin and epinephrine stimulate the uptake of potassium by cells. So insulin and epinephrine will cause an increase in your potassium intracellular levels. And we know if our potassium levels get too high, we have things like aldosterone to cause us to secrete the potassium in our urine to help drop it. So just like water and sodium, your potassium levels are regulated. And just like water and sodium, you can have imbalances in your potassium levels. Pretty similar to sodium. It's either too high or too low. When you have too much potassium in the blood, in your bodily fluids, we call that hyperkalemia. This is dangerous because if you have too much potassium, that will throw off things like repolarization, and you might not be able to excite cells. On the other hand, if you have very little potassium in the body, we call that hypokalemia. You usually see this in diuretics. Remember, you could pee out potassium. So when you have a lot of diuretics, they also cause you to excrete a lot more potassium than you normally would because you're peeing more than you normally would. And again, this is a problem because, again, it's going to affect that repolarization as well. So again, you got to keep everything in its homeostatic range. And yet again, there are still more ions. And again, these are still important ions. Still ions we've talked about before, like these two, calcium and phosphate. Oh, we've seen calcium all over the place, like in our bones and our muscles, and we've seen phosphate in things like adenosine triphosphate, helping to give us energy. So we've seen these before. And you might recall, calcium has a slightly positive charge, while phosphate actually has a slightly negative charge. An ion that has a slightly positive charge is called a cation. So calcium is a type of cation. It has a positive charge. While ions that have a negative charge are called anions. So phosphate is a type of anion. And again, we've already seen where we've used these two ions. We've already seen way back in muscles, you needed calcium to bind to troponin to cause troponin and tropomyosin to move away from actin so that you could have a muscle contraction. We've already seen calcium helping with that plateau phase in our cardiac action potential cycles, as well as helping with cellular signaling. Remember, a neuron will release a neurotransmitter at the synaptic cleft after calcium has entered into the axon terminal. So we've seen calcium is very important. And so as calcium levels change, we will see effects on other things. Turns out, as calcium levels rise, neurons become less permeable to sodium. And vice versa. When your calcium levels drop, neurons become more permeable to sodium. You got to kind of think, you got to balance out even the charges. So if you have a lot of calcium, which already has a positive charge, well, you're going to lower your need for sodium because that has a positive charge. You could even have homeostatic imbalances of charges. So if you have one homeostatic imbalance of one ion, that could actually affect a lot of other ions. And like usual, you're going to have to regulate their levels. You, again, already know how. We're talking about things like calcium. So you're going to have to talk about things like bone or the distal convoluted tubules. And same thing for phosphate. Think about things like bone and also things like your intestines. You know there are homeostasis kind of thing. Calcium. Remember, when your calcium levels get too low, your body's going to notice and force you to raise it. You remember how? Remember this involved a hormone called parathyroid hormone. Remember, when your calcium levels get too low, your thyroid gland notices and releases parathyroid hormone, which will raise it. And you remember parathyroid hormone went to 3 places. Remember, it went to bones to stimulate osteoclasts to break down bones and release calcium to raise it. Remember, it went to the kidneys to inhibit calcium secretion and promote reabsorption, so you'll hold on to calcium and raise your levels. And it even increased calcium absorption in the intestines. You remember that from AMP1. And you even know the opposite for when calcium levels get too high. Remember, when your calcium levels get too high, your thyroid gland notices and releases a hormone called calcitonin, which will decrease it. You remember, calcitonin went to the bones also, in this case to stimulate osteoblasts to build bone and use the calcium to do it, which will drop your calcium levels. And calcitonin also went to the kidneys now to promote calcium secretion and inhibit reabsorption, so you pee out the calcium and drop your calcium levels. And never forget, your ingestion of these things matter. Your diet matters. You can have a lot of calcium in your diet or not. So you already actually knew about calcium homeostasis. However, when it comes to phosphate, it's like your body doesn't really care that much. How? Your body doesn't regulate phosphate ion concentrations the way it does with calcium using fancy hormones. You regulate your phosphate ion concentrations actually pretty closely with your calciums directly. How? It's because they could bind together. Phosphate ions could bind to calcium ions to form what we call a calcium phosphate salt. And when you do this will also affect both their levels. When they bind together, you have less calcium and phosphate because they bound together. And when you unbind them, it's like you've raised their individual levels. So it's kind of like phosphate ion concentrations are regulated almost through calcium levels. And again, you know how to regulate calcium levels. All these slides are kind of reviewing what we already know. We know there are major hormones involved in regulating calcium levels. We'll go through them in the next couple slides. Like this one here, parathyroid hormone. This is us remembering what I just mentioned not too long ago and what you already knew from ANP1 and from endocrine system this semester. One more time. You already know when your calcium levels drop, your parathyroid glands are going to notice and they're going to release parathyroid hormone. And that hormone is going to raise the calcium levels by going to 3 major places. It's going to go to the bones. Remember, in the bones, it's going to stimulate osteoclasts and break down bone. When you break down bone, that will release calcium. And you will raise calcium levels. Remember, another way to do it is to make sure you're not peeing it out. So parathyroid hormone is going to go to the kidneys, inhibit calcium excretion, and promote calcium reabsorption. So you will again raise your calcium levels. And it will also go to the intestines to stimulate calcium reabsorption, all to raise your calcium levels. And it turns out it could also activate vitamin D synthesis and increase phosphate levels as well. Why? Because phosphate reabsorption in the kidneys, or in the intestines, calcium absorption in the intestines will also be increased. But again, stick to just parathyroid hormone and calcium. Parathyroid hormone will raise calcium levels. And like your other ions in water, you could have homeostatic imbalances. And again, just like the ions, it's really simple. Just talking about calcium, you could have too much calcium or too little calcium. Too much calcium is called hyperkalemia, and too little calcium is called hypokalemia, and we will see problems. Think about where you see calcium. For example, if you have too much calcium, hyperkalemia, remember your neurons are going to become less permeable to sodium. And when that happens, sodium is not really going to cross the membrane. And when that happens, you're not going to be able to depolarize. So when you have too much calcium, when you have hyperkalemia, you might see some nervous system disruptions because you're not going to be depolarizing and making action potentials. But on the other hand, if you're hypokalemic, if you have very little calcium, now your neurons are going to increase their permeability to sodium. So you're going to get tons of depolarization. Your nervous system is going to look like it's gone crazy. It's going to seem hyper excitable. It's going to seem like you're agitated and very irritable. You're on alert because your neurons are firing super easily because you have very little calcium. Remember, if you have imbalances of one ion, it will affect other ions. And so we could see some of this clinically. Remember, if we know anatomy, we could take advantage of it. When somebody is hypokalemic, very low on calcium, their neurons are going to increase their sodium permeability and lead to more depolarization and more nervous system stimulation of things like muscles. And you could see things like carpopedal spasms. That's spasms in the wrist and foot and ankle. That's what you're seeing in this picture here. This person may be suffering from some hypokalemia, and you're seeing this spasm in the wrist area. It's a type of sustained contraction. Remember, sustained contractions are what we call tetanus or tetanic contractions. So you'll see that when you don't have enough calcium, almost like a severe Charlie horse. Yeah. But we got to keep going. Remember, you have other things dissolved in the fluid in your body. Remember, earlier in this chapter, we talked about things like acids and bases. You got to talk about your pH. I mentioned earlier, your body likes a pH closer to neutral, closer to 7. Well, if I were to check your bodily fluids, it's really around 7.35 to 7.45. I want you to know that. A normal body pH is between 7.35 and 7.45 in pH range. And how do we keep it there? Remember, we're going to do things like drink our lemonades, which are really acidic, or eat our cookies and cakes made from baking soda, which is alkaline, but we're not swinging to either an acidic or a basic pH. We're staying in this neutral range. You know how. It's with buffers. Remember, buffers resist large swings. So it's really buffers that are going to help to regulate and maintain our pH levels, despite all the acids and bases we have in our body. So what is a source of some of these acids and bases? Well, what about acid? Well, what are some sources of acids in the body? Well, some you know and some you might not know. Well, one major source of acid in your body is actually carbon dioxide. Oh yes, that gas you breathe out is a type of volatile acid. A volatile acid is just an acid that could change its state from things like a gas, which carbon dioxide can be, carbon dioxide gas that you breathe out, or it could transform into more of a solid form like carbonic acid, which you could eliminate in your urine and your kidneys. So carbon dioxide, because it could turn into carbonic acid, is a major source of acid in your body. But it's not the only one. You also have lactic acid, which you get from glycolysis or anaerobic respiration. Remember, glycolysis, aka anaerobic respiration, is you breaking down glucose for energy without oxygen. And it turns out you're going to get byproducts like lactic acid. Or when you break down nucleic acid, you could get byproducts like uric acid. Or when you break down fats, you could get byproducts like ketone bodies. These are all acids in your body. And these acids don't change into a gaseous state like carbon dioxide. They are stuck in their state that you're going to have to eliminate in your urine. They're what we call fixed acids, aka non-volatile, meaning they don't turn into a gas. So these are some of the sources of acids in your body. And again, even though you have a lot of acids in your body, you're not acidic. Why? You have buffers to resist the large swings. And how? You know from AMP1, remember, buffers could weaken strong acids and strong bases. And so if you have a lot of acid, it will be weakened in your body by the buffer systems. Or if you have a strong base, it will be weakened in your body by the buffer systems. How? Think back to AMP1. Remember, buffers kind of act like an acid and base in one. It's like a weak acid and a weak base in one. How? If you were to drop a buffer in a strong acid, it will act like a base to neutralize the acid. Remember, those hydroxyl groups from the base will bind the hydrogen ions from the acid to form water. So if you drop a buffer in a strong acid, it will act like a base to neutralize the acid and form some water. And something similar for a strong base. If you have a strong base and you drop a buffer in it, that buffer is going to act more like a weak acid to neutralize the base and form water. So you don't have a huge swing in your pH. That's all you're seeing on this picture here. They act like the opposite of what you drop them in to help weaken them and reduce large swings in pH. And you might recall the major buffer in your body. It was bicarbonate. Remember, bicarbonate was a major buffer. And bicarbonate you get from carbonic acid. Bicarbonate is called the weak conjugate base to carbonic acid. This is a buffer. Remember, buffers can act like an acid and a base. So this buffer is part of carbonic acid and bicarbonate, depending on what you put in it. If you were to drop this carbonic acid bicarbonate buffer in a strong acid, it will act more like bicarbonate to neutralize the acid. If you drop it in a strong base, it will act more like carbonic acid to neutralize the base. This is a buffer, and that's all buffers do. But it's not the only buffer in your body. Turns out you have a phosphate buffer system. Again, this is a buffer, so it will act as part acid or base depending on what you put it in. So what's the acid and the base in this buffer, phosphate buffer system? Well, the acid is called dihydrogen phosphate. Di for two because it has two hydrogens in it. So when you drop it in water, one of those hydrogens will pop off and become the positively charged hydrogen in your acid. And then the base is just plain old hydrogen phosphate. It only has one hydrogen. So when you drop hydrogen phosphate, it will break up and release the hydroxyl group, the OH group. So depending on if it's exposed to too much acid or too strong of a base, it can help to neutralize them. So phosphate can act as a buffer, this phosphate buffer system. And again, it's not the only buffer system. You got one more. You got a protein buffer system. Proteins can act as buffers based off their R groups, their functional groups. Turns out, again, it's just part acid and part base, but it's all in a group we call the carboxylic acid group. Carboxylic acid groups. And these carboxylic acid groups are acids, so if you expose them to a base, they can neutralize them. But they can also get ionized into their base forms, which can weaken acids as well. So even these protein-based groups can affect your acid-base homeostasis. So when you think about maintaining your pH levels, yes, you got to think about your buffer systems, but you got to think about your acids and your bases. And you got to think about acids and all the different types. And you got to remember that the major acid in your body is carbon dioxide. And it's a volatile acid, meaning it could change into a gaseous state. So when we talk about regulating pH, we got to talk about regulating it with the respiratory system, because you could eliminate carbon dioxide with your gases you breathe out. And you got to think about it being in its solid form, like the fixed acids that need to be eliminated using the renal system. So when we talk about buffers and regulating pH, you're using it in the respiratory and renal systems. And we're gonna have to go into it. And again, these are all kinds of negative feedback. If things get too high, you're going to drop them back to their normal levels. Or if things get too low, you're going to raise them back to their normal levels. And again, you're going to have things like receptors that notice, a control center that comes up with a plan, and effectors that help to put it into effect. So let's look into it. How do things, for example, like the respiratory system, affect our pH homeostasis? How do they affect it? Through things like carbon dioxide. That's how, because this is respiratory system. You're either breathing in oxygen or blowing out carbon dioxide, and oxygen doesn't really count here. It's the carbon dioxide. So what happens? When you're breathing in and out, you're, yes, having to take in oxygen and get out carbon dioxide. And the amount of carbon dioxide you're getting out of the body needs to match what you're making. Remember, we're always following that principle of mass balance. What comes in has to be balanced by what comes out. And you're making carbon dioxide in chemical reactions in your body. So you're breathing it out to match the amount you're making in with all these metabolic reactions happening. And when do you make it? We saw back. You make carbon dioxide when you break down sources of nutrients for energy without very much oxygen. When you do things like glycolysis, aka anaerobic respiration. When do you have a lot of glycolytic reactions going on? When do you do a lot of anaerobic respiration? Well, it's when you're working out. When you're huffing and puffing and doing your workout, yes, part of the huffing and puffing is you getting in oxygen to deliver to your muscles to make energy so you can work out. But another part of it is when you're working out, you're breaking down things like sugar for energy also. And you're going to make things like carbon dioxide. And it turns out you're going to have to get rid of it. This is one reason why you increase your respiratory rate when you're having physical activity. That physical activity is relying on things like glycolysis, glycolytic reactions to make energy, and you're making acids like carbon dioxide, which you're going to have to get out the body so you breathe faster. Well, on the other hand, when you're relaxing, you're not really working out, where you don't need that much energy. You're going to have a decrease in all these chemical reactions and produce less carbon dioxide. That's why when you're relaxing, in addition to not needing that much oxygen, you're not producing that much carbon dioxide, and you don't have that much you're going to have to get out. So just by breathing faster or slower, you could affect your body's pH. And that's how respiratory system will help. Just by either having you breathe faster and get rid of carbon dioxide, or breathe slower and not get rid of it that fast. But also, don't forget, there's also the urinary system, the renal system. Remember, you could pee out acids and bases. And when it comes to the urinary system, we already know we could secrete positively charged hydrogen ions directly. We could secrete acid directly in our urine. And you know now, you could also secrete carbon dioxide in its carbonic acid form. And they're related. Turns out when you secrete those positively charged hydrogen ions, it will bind to bicarbonate. And when it binds to bicarbonate, it forms that carbonic acid, which will carry also that carbon dioxide. And then eventually you'll break them apart using an enzyme called carbonic anhydrase. It will take that newly formed carbonic acid and break it back up into its carbon dioxide and now pure water form from that original positively charged hydrogen and bicarbonate. And then once you're in the kidney tubules, that carbon dioxide and water actually reforms the carbonic acid. And this is also controlled by carbonic anhydrase. So your body is going through this process of forming and unforming carbonic acid to help move around the hydrogen ion and carbon dioxide, depending on if you need to get rid of it and hold on to it. So your kidneys, again, could either cause secretion or reabsorption, and they will bind and break apart with the help of carbonic anhydrase. Like always, we're going to have to look into this with a little bit more detail. I told you in the kidneys, well, really the proximal convoluted tubules of the kidneys, you could secrete acid. And I told you when you secrete that acid into the filtrate, it will bind to bicarbonate. But where did the bicarbonate come from? You get it from other things. You get it from glutamine. When glutamine enters a cell, it'll get broken down into byproducts. It'll get broken down into ammonia, which you'll pee out in your urine, and into bicarbonate. And that's where you're getting the bicarbonate that the hydrogen ion will bind to. But this hydrogen ion isn't really that picky. Turns out, yes, it could bind to the bicarbonate to form your carbonic acid, which will move around. But that positively charged hydrogen ion could also bind to the ammonia. When hydrogen binds to ammonia, you get ammonium ions, and that's really what's peed out. When we say you pee out ammonia, you're really peeing it out in the form of these ammonium ions, where it's bound itself to some of these positively charged hydrogen ions. And at the same time, that bicarbonate will move around as well, moving around the carbon dioxide, possibly going to the lungs where it will dissociate, break apart, and cause you to breathe out the carbon dioxide. Or, like we mentioned before, it will go to the kidneys and bind to hydrogen ions to form carbonic acid that you could pee out. And that's all you're seeing on this slide. You'll move your positively charged hydrogen ions and your carbon dioxide in the form of carbonic acid and bicarbonate. And all of that was happening in the proximal convoluted tubule. But that doesn't really give you a lot of acidic urine, because you see a lot of this is recycled. You're mainly moving it around from place to place between cells and filtrate. When we talk about adding acids to the urine, we call that acidification of urine. And a lot of that acidification of urine occurs in your kind of what we call the late distal convoluted tubule, meaning the ends of the distal convoluted tubule. And it's really the cells that are helping to do it. The cells in the later part of the distal convoluted tubule and the early parts of the collecting duct. We call these cells intercalated cells, like intercalated discs. These cells are primarily responsible for acidifying the urine, transporting that positively charged hydrogen ion into that filtrate that will become the urine. And how? It's just by binding itself to carbon dioxide, like we mentioned before. Carbon dioxide will diffuse from your blood into the interstitial fluid around those intercalated cells. And when it's there, it will react with any water to form carbonic acid. And that carbonic acid will then itself break apart into its positively charged hydrogen ion and bicarbonate. And that positively charged hydrogen ion is what's going to get transported into the filtrate. So it's a lot of shuffling around to get you to get rid of the acid. It all starts off with the carbon dioxide. Then it will bind itself to water to form carbonic acid. Then the carbonic acid, thanks to carbonic anhydrous, will break apart into positively charged hydrogen and your bicarbonate, and you will drop off the hydrogen in the urine and pee it out. This is the major source for acidification of urine. And that's all you're seeing. Carbon dioxide from the blood, bind it to water to form your carbonic acid. Then use your carbonic anhydrase to break it apart into its bicarbonate, which will go back into the bloodstream, and the positively charged hydrogen ion will get pumped into the filtrate, which you will pee out. And like always, even for acid and base levels, your body will try to maintain homeostasis, but you can have some imbalances. Sometimes, yes, your body will have too much acid or too little, or too much base or too little. And like always, your body's going to try to restore homeostasis. We give a name to this. When your body tries to restore your pH levels homeostasis using the respiratory or urinary system, we call this compensation. You have compensatory mechanisms. If your respiratory system is trying to restore your normal pH, we call that respiratory compensation. If your urinary system is trying to restore your pH, we call that urinary compensation. But sometimes they don't do it successfully and you get an imbalance. For example, you could have too much acid in the body. We call this acidosis. And you will see this as a low pH. You'll see this as a pH less than our 7.35. And like always, you got to talk about fluid pockets. When you talk about having an overall body acid level, too much acid, low pH, that's acidosis. But we can narrow it. If we talk about just the low pH of just the blood, we call that acidemia. So low pH overall, too much acid overall, acidosis, or low pH just in the bloodstream, too much acid just in the bloodstream, call that acidemia. And how do you get acidosis and acidemia? Well, in general, overall, the reason why you're so acidic is because you've probably outpaced your buffer system, meaning you had way too much acid for your buffers in your body to handle, and that's why you're acidic. What could cause that? There are lots of things. So keep it in general. You had too much acid, it overwhelmed your buffer system. And you'll see changes. You'll see problems with acidosis, too much acid. Turns out when you have a lot of acid, aka acidosis, your neurons become less excitable, meaning they make fewer action potentials. They don't depolarize, they don't make action potentials. And you would see this as your nervous system getting what we call depressed, meaning it's not working as much or as often as it seemed to before. Why? Because your neurons just aren't as active. Why? It's too acidic. And so, like I mentioned before, if you have an acid-base imbalance, you're going to have compensation. So let's go through it. For example, how do you get this acidic, for one example, and compensate for it? Well, one cause could be a respiratory cause. We call it respiratory acidosis. Kind of tells you in the name. You're having acidosis because of the respiratory system. How? Oh, you remember the major acid in your body is carbon dioxide, and you could breathe it out. And if you breathe it out, that's you getting rid of it. So if you're having acidosis, too much acid, maybe you're not getting rid of it. Oh, how do you not get rid of enough carbon dioxide by breathing? Well, it's if you don't breathe that much. If you decrease your ventilation rate, your respiratory rate, we call that hypoventilation. Hypoventilation, breathing less or slower, is a major cause for acidosis. We call it respiratory acidosis. Why? Because you're holding on to carbon dioxide. You're holding on to that acid, and it's going to lower your pH. Why? Because remember, that carbon dioxide has another form, carbonic acid, which it can transform into. And what could cause you to breathe less? Well, maybe you have a brainstem problem. Remember, breathing is a reflex controlled by the medulla oblongata, at least the rate of breathing. So if there's a brainstem problem, a medulla oblongata dysfunction, well, you might breathe less and have acidosis. Or maybe it's a respiratory system problem. Maybe you have a blockage in your airways, not allowing you to move air and ventilate. Well, of course, you're not going to move the air and you're going to have acidosis. Or maybe it's an alveoli problem. Remember, your alveoli are responsible for doing the gas exchange. So if they don't work properly, you're not going to do gas exchange, you're not going to get rid of carbon dioxide, and you will have acidosis. But hold on, don't worry. Hopefully, you will compensate. Hopefully, you will have a feedback mechanism to restore homeostasis. How? Well, you will immediately have a compensation in the respiratory system. You will immediately start a respiratory compensation within minutes. How? Turns out chemoreceptors in your brain are going to notice very quickly within minutes when you become too acidic. And they'll simply just increase the respiratory rate. Chemoreceptors in your brain, remember, some are in your medulla. So they'll notice and then have a reflexive hyperventilation. They will increase the rate to hopefully restore the homeostasis. But even though this happens quickly, it's not that effective. Just by getting you to breathe faster, it's not going to do as well of a job of correcting the newly created acidosis. Turns out your renal system will do a better job. You'll also have a renal compensation, which will do a better job. How? Is you know the answer already. You're going to pee out the positively charged hydrogen ions. You're going to pee it out, and that's going to have a greater effect because you're peeing out directly the acid. Remember, you're going to take the carbon dioxide from the blood, have it bind water to form carbonic acid, then use carbonic anhydrase to break that into your positively charged hydrogen and your bicarbonate, and you'll pee out the acid. But even though you're directly peeing out the acid and it's a better way to compensate, it takes longer. It takes minutes to hours and in some cases days to go through those steps of turning that carbon dioxide, enough of it, into that carbonic acid and then breaking that into the positively charged hydrogen acid and the bicarbonate. That takes time. So even though renal compensation is more effective because you're going to eventually directly pee out that extra positively charged hydrogen ions, it takes a long time to do it. But remember, carbon dioxide is not the only acid in the body. So you could have acidosis from other causes that are from other acids, fixed acids, non-volatile acids, acids that cannot become a gas. So you're not going to use the respiratory system. So these types of acidosis are called metabolic acidosis. So you're getting your extra positively charged hydrogen ions from another acid other than carbon dioxide and its carbonic acid form. Oh, you know the answers. Remember, what are other sources of acids? Remember, it's ketone bodies from breakdowns of fat, or uric acid from nucleic acid breakdown, or lactic acid, etc. These are your non-volatile acids, and if you get too much of them, you could get an acidosis. But there are other reasons for an acidosis. You could also get it in diabetics who are experiencing a diabetic ketoacidosis. When you're diabetic, remember, you're not really breaking down glucose for energy because you don't have enough insulin, or your body's not listening to the insulin. And you'll use other sources of energy. You'll use fat and get ketone bodies that are acids. That's why we call it diabetic ketoacidosis. You're seeing a diabetic breaking down fats instead of sugars and getting lots of ketones. So they get acidosis, which is a type of metabolic acidosis. You could also get it if the kidneys fail to secrete your acid, or if you kind of get rid of your buffers, like bicarbonate. Oh, how do you get rid of buffers? Turns out it's with things like chronic or prolonged diarrhea. Chronic or prolonged diarrhea can lead to you, yes, literally pooping out too much bicarbonate and lowering your bicarbonate levels. And this will cause or potentially lead to a acidosis. But again, don't worry. If you have an acidosis, you will try to compensate. Oh, how would you compensate now for a metabolic acidosis? Well, same ways. You'll have a respiratory and a renal compensation. And again, you just like before, the respiratory compensation is the faster one, happens within minutes. How do you get rid of acid? Remember, you hyperventilate. Breathe faster, you will blow out carbon dioxide. And you will still also do a renal compensation. Even though you could have a possible acidosis due to you not secreting enough acid, there are other causes. And those other causes can hopefully be compensated by a functional kidney where you do adequately eliminate the acid. So like always, this is a type of negative feedback mechanism. If your pH gets out of range, either too high or too low, you'll go in the opposite direction to restore the homeostasis. So you'll notice when your respiratory rate increases, aka hyperventilation, that could help you to restore homeostasis. It could help to correct an acidosis. But you're not really fixing the problem. It's just correcting the pH imbalance. So if you have a metabolic acidosis, that respiratory compensation where you're hypoventilating is only helping to correct the pH imbalance. It's not correcting the original source of the metabolic imbalance. So you'll have to ultimately fix that. And that's acidosis. And again, this is anatomy. If you can have an acidosis, well, you can have an alkalosis. You can have too high of a pH. You can have too much base in the body. Remember, an overall high base level or too high a pH, that's called alkalosis. And if we're talking about specifically the blood having too high of a pH or too much base, is called alkalemia. And you'll see the opposite effects to acidosis. Remember, acidosis depressed the nervous system. Alkalosis will seem like it's a stimulant for your nervous system. Why? Because when you have an alkalosis or alkalemia, your neurons increase their excitability, meaning they're going to make more action potentials. So you're going to see things like possibly seizures. You're seeing too many action potentials, or maybe motor symptoms. You might have twitching or spasms for no reasons, or tingling, or possibly numbness. Numbness is also a result of neurons firing. You'll see lots of weird nervous system symptoms in alkalosis or alkalemia as well. And again, don't worry, your body will try to compensate both respiratory ways and with renal or metabolic ways. We're going to have to talk about both the respiratory and metabolic alkaloses and their compensations. And you remember, alkalosis is almost pretty much the opposite of acidosis, if that helps. So now let's think about it. First is respiratory alkalosis. It's kind of the opposite of acidosis. Remember, you have respiratory acidosis because you're not breathing fast enough. You have hypoventilation leading to you holding on to the carbon dioxide and holding on to acid. Well, if you have respiratory alkalosis, it's the opposite. It's due to you breathing too fast. You're having a hyperventilation. So you're kicking out lots of carbon dioxide and losing acid. And you're going to see that as you being more basic, having a lot of base, you having alkalosis. Well, you could have a psychological hyperventilation, psyche, that's you mentally. You could try to hyperventilate, but you won't really see an alkalosis because you're going to have a rapid response. How? Your brain's going to override you. You're going to lose consciousness and your brainstem is going to adjust your respiratory rate. So, if you tried huffing and puffing for too long for no reason, you might pass out, and that's your brain taking control. Remember, your body thinks you're stupid. It will protect itself from you. While at the same time, your kidneys are going to force you to excrete bicarbonate, excrete those buffers that might try to neutralize acids so that your acid levels can raise and restore the pH. And it will also hold on to positively charged hydrogen ions for the same reason. Hold on or inhibit positively charged hydrogen ion secretion and excretion in the kidneys, aka don't let you pee them out, so you can restore the pH, because you're too alkalotic right now. And then you could have metabolic alkalosis. Now, this is not you breathing. This is metabolic. How do you have a metabolic alkalosis? Well, it could be because of one of two reasons. Either you're losing acids. How do you lose acid? Well, you can vomit. When you vomit, you're losing some of the acid from your stomach. That could lead to a metabolic alkalosis. Or, on the other hand, you can have too much of a buffer, like bicarbonate. How do you have too much bicarbonate? Well, it's in things like antacids. Think things like Tums. Well, you could abuse Tums, believe it or not. You could have an overuse of antacids like Tums. That's you taking in too many buffers like bicarbonate that will neutralize too much acid and cause an alkalosis. Now, these are causes of metabolic alkalosis, either losing the acid or having too much buffer. And again, you will compensate both with the respiratory system and the renal system. You're alkalotic now. You're too basic. So if you're too basic, the respiratory system will cause a hypoventilation. So you hold on to the carbon dioxide and acid and hopefully restore the pH. While at the same time, your kidneys will hold on to the positively charged hydrogen ions and cause you to secrete and pee out the bicarbonate to restore the pH. And like always, if we know anatomy, we could take advantage. If we know that we could have some disturbances in our acid base levels and there's compensation, I could look at your body and tell what's going on. How? I could take some of your blood and look at things like your pH level, your carbon dioxide level, your acid levels, and your bicarbonate levels. How? By checking your blood. Mainly your arterial blood, the blood in your arteries. We call that your arterial blood gases, or ABGs for short. When I check your arterial blood gases, I'm checking the blood in your arteries to measure your pH, how much acid, your carbon dioxide levels, your partial pressures of carbon dioxide levels, as well as your bicarbonate levels. And by looking at those three major things, I could tell what type of problem is going on, what type of imbalance. Is it an acidosis or alkalosis? And I could see if there's also compensation. And your body doesn't always compensate. Sometimes you have an uncompensated imbalance. Sometimes you might have a partial imbalance. We're not going to focus on uncompensated and partial. We're going to focus on how do you tell whether or not you have an acidosis or an alkalosis and if there is compensation. That's what you're seeing as the last two bullet points on this slide. For example, if you have a respiratory alkalosis, we know this. We're just putting it all together now. So you know what you should see when you are having the ABGs, the arterial blood gases of someone with respiratory alkalosis. What? Well, their alkalosis. So you're going to see a high pH when you check their ABG. And this is respiratory alkalosis. Remember, this is because they're breathing too fast. So you're going to see very little carbon dioxide in their blood. And remember, when you have a respiratory alkalosis, you're going to have compensation in the kidneys. How? They're going to force you to pee out your buffer, bicarbonate. So you will see a low bicarbonate. Those three things are a sign of respiratory alkalosis: a high pH, a low PCO2, partial pressure of carbon dioxide, and a low bicarbonate because you're having renal compensation. Same things. I should be able to see the signs for metabolic alkalosis. Again, take it step by step. It's an alkalosis, so the pH in your ABG is going to be high. Remember, this is a metabolic alkalosis. Remember, this is either due to very little acid or too much bicarbonate. So when I check your ABG, I'm going to see a high pH and a high bicarbonate levels. And you're going to have some compensation in the lungs. How? It's going to cause hypoventilation to cause you to hold on to carbon dioxide. So I will also see a high PCO2. So if I see these three things, a high pH, a high bicarbonate, and a high partial pressure of carbon dioxide, high PCO2, well, you're undergoing metabolic alkalosis. Look at that. I told you, I got to give you a little baby doctor degree at the end of this class, because now you know how, or at least to check for signs of homeostatic imbalances and their compensation. That's all this slide is summarizing. Make sure you could identify these different types of disorders based off the changes in pH, in carbon dioxide levels, and your bicarbonate levels. One more time, this one slide summarizes it. There's respiratory acidosis, respiratory alkalosis, metabolic alkalosis, and metabolic acidosis. Take it one step. All the acidosis problems will have a low pH. All the alkalosis problems will have a high pH. Then it's a question of whether or not it's respiratory or metabolic. If it's respiratory acidosis, again, low pH acidosis, respiratory, it's because you have a high PCO2. If it's respiratory alkalosis, again, it's alkalosis, so high pH. If it's respiratory alkalosis, it's because of a low CO2. And then there's the metabolics. Metabolic acidosis, again, acidosis, so low pH. And it's metabolic because you either have too much acid or low bicarbonate. And metabolic alkalosis is because of a high bicarbonate level, causing your high pH. So make sure you know these differences and the differences you're going to see in your pH, bicarbonate, and possibly carbon dioxide levels. And that's the end to chapter 25.